That's gonna take a lot of paper towels. Just be careful not to slip on the floor. I'm gonna go ahead and get started. So let's just leave that be. All right, guys, welcome. Hello. Hope everybody is doing great today. We are on the brink of the end of the semester here, and hope that you're keeping your sanity during this very, very busy time. Going to start off today with a few announcements, and then we'll jump in to section 9.5 again today. I pulled up on my screen the Canvas page for the class here, and just want to remind you about this. Be careful as you come in. There's water on the floor. So the midterm is on Monday, our next midterm, and it's going to cover the sections that are listed right here. So chapter 6, don't forget that goes back a few weeks. That's where we learned about linear transformations, kernel, range, one-to-one and onto transformations, isomorphisms, right? So that goes back. Let's go back and refresh our memory on some of that perhaps. Chapter 7 is the eigenvalue, eigenvector chapter. So here we're learning about everything to do with eigenspaces, diagonalizing a matrix, defective and non-defective, right? All of that's in chapter 7. Chapter 8 is the stuff on the nth order linear differential equations. So of course that forms an n-dimensional vector space, and we can solve the non-homogeneous system with two different methods. Remember what they were? What are the two methods for non-homogeneous nth order linear differential equations? Annihilators, yes, very good. And what's the other one?
Variation of parameters.
Variation of parameters, very good. So that's in chapter 8. Make sure you know that stuff well. And then finally, the more recent material in chapter 9, which we're doing right now, which is having to do with linear systems of differential equations. So that is pretty much what the midterm is going to cover. It is basically everything we've done since spring break. Okay, it's basically since spring break. I will be giving you a table of annihilators and integrals on that test on Monday. Also, just a quick reminder, you can come take the test at noon or during the regular class time right now too. It's your choice, same exam for both times.
Never mind, that's for the final.
Yeah. Let's talk about the midterm first. So for the midterm, it's either 12 o'clock or 2 o'clock. Try to get here a few minutes early. I try to help you out with a few extra minutes at the beginning or the end or both, whatever I can do to give you some extra time. That should be good. Before we get to the midterm itself, don't forget that we have one more homework assignment to get done. It's due on Friday night at 10 o'clock. I have office hours today and on Friday to help you with that. But you will want to do that homework. It's homework number 23. It's your chance to practice the material before you really get into full-blown study mode. Okay, so definitely take some time to do the homework for Friday. Somebody in my other class was asking me which homeworks this exam actually would be related to, and there's quite a few of them. There's no reason to think that you would need to go back and redo all this homework. I would not recommend that. The point of doing the homework was just to kind of learn the stuff in the first place, just to kind of practice it and get the hang of it, right? That was the original reason. But a much better thing to do probably than doing the homework again would be to look at the group works, because the group works are more manageable. They don't take as much time. So I would say group works 10 through 15 would be good to look at for the exam. But I also wanted to just show you here up on the course Canvas page what else is up here for you. Let me point out, if you go to the files section of the Canvas page, can you guys all see that okay? showing up there? So there's a midterm 3 resources folder, and I'm just gonna click it open here for a moment. Oh, so here you see a bunch of things you can look at. There is a sample midterm. I also have the answers to the sample midterm. There's also a review session, solutions to the problems that are in that review session. And then there's just the review packet itself, along with the solutions to some problems in there. Let me point out, if you want to go to see the review session, we can go to the pages section. And down here you see where it says midterm 3 review session. This is just a 3-hour video. So it's completely optional, but if you're interested in watching it, you're certainly welcome to do that. This is actually aligned exactly to the handout that says midterm 3 review session. So if I go back to the other page again, it just doesn't let me put videos in this folder. So that's why I had to go put it in that other page. But yeah, where it says review session here, if you want to watch me solve the video, solve the problems in the review session, that 3-hour video has those solutions to it. Okay. Everybody kind of comfortable about what's, and then somebody in my first class asked me, oh, what about a second sample exam? You might remember for both of the first 2 midterms, I actually ended up sending out an additional sample test. I will do that again for this test. So there'll be another sample exam with solutions that I'll email out to you. Yes?
You know, over the last 2 exams, you gave us 4 extra points for watching videos. Is there anything is there anything?
Is
like
there
that
going
here?
to be any extra credit? If you wait another minute or 2, you're going to find out about that. So just have to hold on for a second. Okay, so far any questions are there? Everybody feeling okay? You know, I just want to say one quick thing, guys. There is more stuff up here than maybe you have time for, right? I know you're all really busy and you know, it's just craziness going on right now. So do what you can and then just let the rest go, right? Just be okay with it. As your professor, I just don't want to get accused of not giving you enough stuff. So I sort of go over the top, I would say, and probably end up giving you too much stuff. But you know, it's better to have too much than too little. Do as much as you can and let the rest go. What I would say is the sample midterm, you should definitely do it because, well, that gives you an idea what kind of problems I'm going to ask, how long it's going to be, the formatting, the balance, everything. I would definitely try the sample test. If you have more time than that, I would probably recommend maybe looking at the group works. The group works would be a good idea as well. Okay. If you have more time than that, I might consider the review session. Okay. And the last thing is the thing that probably would be the last thing I would do in the midterm 3 review packet, which has all this information on it. There are a bunch of problems down here at the end of that as well. Okay, so again, this is maybe more than you want to do. It's kind of up to you. Like maybe you realize, oh, gee, I'm really not very strong on chapter 6. So then you can go through and find where are the chapter 6 problems. This doesn't look like chapter 6, right? So you go find where are some problems about chapter 6 and practice those, right? So you find something where it says something about kernel and range, I don't know, somewhere, should be in here.
Wait, is that last problem?
I'm not finding it right now, but that's okay. There's tons of questions about kernels and ranges. But anyways, you find things that you're weak on and you just go find places to practice those concepts. Okay. And then the solutions to those problems are also there. Oh, I also wanted to remind you guys, I have a bunch of extra office hours. So starting on Friday, well, of course I have office hours today, but also on Friday evening, like I usually do, if you're finishing up that homework and you have some questions, I'll be around Friday evening. I'm going to be around on both Saturday and Sunday in the evening. If I'm able to be available earlier in the day, I will send you a note and let you know through email. As of right now, I'm not sure. So I said 8 p.m. Because I may have some things going on during the daytime. Also on Monday morning, I will be around for about 3 hours until I actually have to come up and start giving the exam. So we have plenty of time to catch me. And if none of this works out and you don't want to deal with me on Zoom or in person, you can also just send me an email and I'll be checking my email pretty regularly. Okay. Any questions about any of that? So one other thing, well, I guess I can turn this down now. Great. One other thing, so as you know, this semester, I just haven't had time to give quizzes because there just has been too much material. And just not a great use of the precious minutes that we have together. But there was a time when I used to give quizzes, and I was looking over this quiz that I had given a few years ago. But, gee, these are really pretty good questions for practice, like to study for the exam. So what I have decided to do is, and this is an opportunity only for you guys who are actually physically here. I have noticed that there are some students who have sort of started just watching everything on Zoom and not really coming and participating, which I appreciate you guys coming and participating. And so today is your lucky day, because by being here, I'm going to give you this opportunity. There is a number in the top right corner of this handout, and that is just so I don't get duplicate quizzes. So please do not go copy this off for the person that you know that's not here today, because they don't get this opportunity, right? So there's one quiz per number. And what this is extra credit. So here is how this works. It is due on Saturday. I'm making it due Saturday because we have homework that's due on Friday, and I want it to do before the exam because I want you to use it as a study tool. And it is just a quiz. It's just a take-home quiz that you're going to get to do. You can ignore the point values because these are, I should have just deleted those. What I'm basically going to do, there's 4 problems here. You're going to get 1 point for each correct problem. Now, if you get half of it correct, you'll get half of a point. And then you'll also get just 1 point just for turning it in. So in Canvas, there will be a slot in the assignments section of Canvas for you to turn this in by Friday night. You can get up to 5 extra credit points for the midterm by getting these 4 problems right, plus turning it in. Okay, does that make sense? Okay, let me start passing it out. Go ahead.
When by Saturday?
What's that?
When by Saturday?
At 10 p.m. It's always 10 p.m. And again, this is only for you guys because you're here today. You picked a good day to not skip class. Go. I mean, technically, there's still 30 people enrolled in this class. Where everybody is. So, yes. I'm sorry. I'll have to talk to him separately. Most likely not. Okay. So please don't work on that right now, but you can have 3 days to work on it. It shouldn't take you that long because I actually did give that as a quiz during class one time, and it's like 20 minutes, 30 minutes, something like that. So it's just good practice, just one more good thing to practice before the test that we're going to take on Monday, okay? Once we get past Saturday night, I'll send you the answers to the quiz as well, so you'll have that to look at. So with that, does anybody have any questions regarding the exam on Monday? Have I hopefully addressed it all? I have not written the test yet. That's why I'm saying the best thing to do is to look at the sample tests, because you probably noticed with the first 2 midterms, the sample midterms and the actual midterm, they were obviously not the same, but the kinds of questions were similar. So it makes sense that that's a good thing to look at. Okay, well, what are we going to do today then? What we're going to do today is really not really do much new material at all. We're going to mainly be practicing the stuff that we did a pretty heavy lecture on Monday, you might remember. So today I'm going to try to keep it more example oriented, and there won't be a lot of new material. I do on the sideboard over here have a recap of what we did on Monday. Just to kind of remind you here, we're working on defective linear systems. So if you have a matrix for your linear system that happens to be defective, again, what does that mean? That just means that there's an eigenvalue out there that does not pull its weight. Okay, so if you have that scenario, then we still want to be able to solve the linear system. So I promised you I would only do 2 by 2 or 3 by 3 examples for this particular section. And on Monday, we did the 2 by 2 case. I said, suppose you have an eigenvalue, lambda. It shows up here twice, but only gives me 1 eigenvector, right? So it fails to pull its weight. With me? So far, so good. We have a defective system. It's the same lambda twice, but only one eigenvector. It's not pulling its weight. So then how do we get two linearly independent solutions to our system? That's what's in the box right here, right? We build this, e to the lambda t times v. That's kind of the first solution. Just write that down. But then on Monday, we talked about, well, how will we get a second solution? It's called x2, and here is what we came up with, right? We actually derived that if we take e to the lambda t times w1 plus t times w2, we can build, that second solution. And the rules about the w1 and the w2, the best way to remember the rules is to look at this diagram right here at the bottom of the board. We're going to choose W1. Okay, so you're choosing W1 over here on the left. When you remember, every time you go across an arc, it means multiply by a minus lambda I. So once you have W1, you don't get to choose W2. You actually form W2 by applying a minus lambda I to W1. W2, when you apply a minus lambda I to that vector, you have to get 0. Okay? And the fact that you have to get 0, I kind of reminded you up here at the top of this board. If you apply a minus lambda I to W2 and you get 0, when I rearrange that equation, what I recognize is that W2 is just an eigenvector. AV equals lambda V, right? So that W2 is like an eigenvector here. Okay, so on Monday, we did this 2x2 scenario. We did an example and kind of practiced how that diagram works. Before I go on, because today I'd like to do some 3x3 examples, are there any questions about sort of the overview of this process that I've got on the board here? So far, so good. If we're good so far, I'm going to go ahead then and we're going to talk about, actually, I'll just use this board here. We're going to talk about the 3x3 linear, defective linear systems. And in this case, it's actually a little bit more complicated. Okay, so let's do that here. So let's look today, we're going to focus on the 3x3 case. We take a 3x3 linear system. Now, it turns out that there are multiple ways that a 3x3 could be defective. For example, you might have, so let's do case 1 here. Case 1, you might have a lambda 1, let's say, and then, of course, it has a corresponding eigenvector, let's say V1. And then let's suppose that you have another lambda, I'm going to call it lambda 2. But let's suppose that that lambda only produces one eigenvector, which I'm going to call V2. So notice that lambda 2 shows up twice, right? And I'm imagining that, remember, to have a defective matrix, you have to have repeat lambdas. So suppose that one of your lambdas repeats twice and only gives you one eigenvector. So it did not pull its weight, right? Well, this is what I'm going to call the mixed eigenvalue case. So we're going to have 3 different cases here, guys, and I like to have words to describe the 3 cases. And we're going to do an example today of all 3 cases. So this is mixed eigenvalue. In this case, the question would be, how do you get your solutions? How many solutions do I need to get? It's 3, right? Because it's a 3x3 linear system, and so the solution set is a 3-dimensional solution set. So I need 3 basis vectors. I need 3 basis solutions. So we actually need to write down here on the side. I'm going to do this. We're going to write down what are the 3 solutions that we would have. So the first solution, right? We're just going to use the first lambda. And we're going to write e to the lambda 1 t times v1. So I'm just following the idea of what's on the sideboard there. For the second solution, we're going to use e to the lambda 2 times t times v2. And now to get our third solution, I'm going to use the same idea that we learned on Monday, which is to use the W's. So I'm going to do e to the lambda 2t times W1 plus t times W2. Okay, so this is case one. It's one of the three cases that we can have. It's called the mixed eigenvalue case. Okay, so far so good? We'll come back and do an example of it in a little bit. But before I do that, I want to go on to case two. Case two is actually going to be where you have the same lambda 3 times. But I'm going to imagine here that you actually do get 2 eigenvectors. Let's say V1 and V2. Okay, so again, the eigenvalue has a weight of 3, but is only giving us 2 eigenvectors. That's why it's defective. Yeah, and this is the case, I'm going to call this case regular defective. This is what I will call regular defective. And again, I want to write down how we're going to get 3 solutions here. So we're going to have, in this case, x1 of t e to the lambda t times v1. Okay, so that's the first solution. And then the second solution would, of course, just be x2 of t is e to the lambda t times v2. So we can write down 2 solutions just in the standard way. And then we have to come up with a third solution. And the x3, this is going to be where we use the w's again. So e to the lambda t times w1 plus t times w2. Okay, so same old story, the w's still satisfy the same picture again. Okay, so this is for a 3x3 defective case. So far so good? Sebastian?
For the V1 and V2, which lambdas make up which one?
There's only one lambda in case 2. Same lambda 3 times. So this is the same lambda. The same lambda is producing both of those vectors.
Oh, okay.
Yeah. So up on the first case, I had to have a lambda 1 and a lambda 2, and I was referencing them separately, but down here it's the same lambda. It's just there's only one lambda that you even have to look at. That make sense? Any other questions so far? You ready for the really scary one? Case 3 is the really tricky one. Yeah, so case 3, this one is where you have only one lambda 3 times, lambda, lambda, and lambda, but you only get one vector out of it. I'm going to call that v. So this is what we are going to call super defective. This is the super defective case. It's because the lambda really fails to pull its weight. It's really coming up short. All right, so in this case, we still need to get 3 solutions. The question is, how do we get them, right? Well, the first solution, x1 of t, you're not going to be surprised. It's just e to the lambda t times v yet again. Same thing we've seen for the last few sections. That's what we would have. x2, all right, well, here we're going to use the w's. So e to the lambda t, and then I have w1 plus t times w2. That's my second solution. That makes sense. But now I still need one more solution. Because I got to get 3, right? I have to have 3 solutions. And I've kind of exhausted my W idea now. So the question is, how do we get a third solution?
Do you turn that parentheses into its own W?
I'm going to show you what we do. It's actually, you'd never guess it. It's actually another one of these really bizarre things. Here's what it is, guys. It's you take e to the lambda t. Okay, that makes sense. And then what you have to do is multiply that by W3 plus t times W4 plus t squared over 2 times W5. This is the one little bit of new material today. Okay. Now, if you're looking at that and you're like, huh, what's he talking about? You're probably with everybody else in the room, right? So there's actually a diagram for this as well. I don't know if you remember, how we derived the W1 and the W2 thing and that diagram. We did all of that on Monday. What I'm basically going to show you here, guys, is a new diagram. And the diagram starts with W3. And you choose W3, and then what we're going to do is we're going to draw these arcs. Every time I go across an arc, I am multiplying by A minus lambda I. And in this case, I get W4 when I do that. And then when I go another arc across, another A minus lambda I, now I'm going to call this result W5. And now, this is a slightly bigger picture, as you can see. We do A minus lambda I for a third time, and now we finally get 0. Okay, so this is the picture for this super defective case. We only need this picture when we're going all the way to the super defective case. We don't need this for the first 2 cases. Again, the way that this works really is somebody way smarter than me figured out that this form of a solution is going to work. And they plugged it into the, remember this is really what's behind everything today, right? X prime equals AX. They took this linear system and they plugged this guess into the left side and into the right side. And they matched up the constant terms and the t terms and the t squared terms. They matched them up on the left and the right. And once they did that, they figured out, oh, here's what has to be true about the W's. Now, the thing with the W's is it's a bunch of equations, right? It's equations like this here. I decided to get rid of that after 20 times of teaching Math 250B. I finally figured out that, in my view, the easiest way to explain it and the easiest way to learn it is through these pictures. These pictures tell you how to do the W stuff that you have to do to get the solution. By the way, there's actually a nice little side effect here of this third super defective case. If you just ignore the first arc, you just ignore the first part and you just look at the last 2 parts, what does it look like?
Like the first example.
It looks like that picture, doesn't it? Yeah, so in fact, it turns out that if you want, you can do the W3, 4, and 5 first. Do this solution first, and then you can go back and say, oh, I am just going to take W1 and W2 to be whatever W4 and W5 are. There's no reason why these really have to be 5 different W's. So the W1 and W2 can just be chosen to line up with whatever you came up with for W4 and W5. And you know that just by ignoring this part of the picture, your W1 and your W2 will do the job that they're supposed to do. That makes sense so far? Guys, that's the only new material for today. It's just this little piece right here. I'm not going to derive it. On Monday, I did derive the one that's on the sideboard over here. I don't want to take you through that again. So it's just more of the same stuff. What we are going to do, guys, is 3 examples right now. And it's going to be 1 of each case. And each of these cases has a little bit of a different feeling to it. So that's why I want to do all 3 cases, because they all have something different to learn. So let's do some examples. We'll probably do 2 examples here at the beginning, and then we'll take a break. And then after the break, we'll do the third one. Okay, so let's solve x prime equals ax, where capital A is the following matrix. It's got to be a 3 by 3. I'm going to use 8, 1, 0. And then -1, 10, 0, and -1, 1, 9. Okay. So there's our matrix. Can somebody tell me what's the first step? What do I need to do first to solve this problem? Get the lambdas. Exactly. I've got to find my eigenvalues. So let me start my solution here. We're going to take the determinant of the matrix that we get when we subtract lambda off of the main diagonal. So I'm just subtracting lambda off of the main diagonal. So today is a nice chance to review chapter 7 as well. We're doing all of that chapter 7 stuff again. Any tips on how to do this determinant?
Cofactor expansion of the third column.
Okay, column 3 has a lot of zeros in it. So that's a favorable choice of a column to expand. And do not use the arrow method. I said that in chapter 7 and I'm just reviewing it again right now. If you use the arrow method on this determinant, you're going to get something that's very hard to factor. And that means you'll have a hard time getting the lambdas. So please do not use the arrow method here. Let's expand column 3. Let's expand column 3. So what you'll have is, see, you have 0 here and 0 here, so I only have to worry about the bottom slot here. 9 minus lambda times the determinant of this 2 by 2 submatrix, which I can use the 2 by 2 formula for. So 8 minus lambda times 10 minus lambda, and then plus 1. There you have it. And again, I don't want to multiply that out, right? You don't want to like fully multiply the whole thing out or you'll get an equation that you cannot easily factor. Instead, let's actually just multiply this out. I get lambda times lambda, and then minus 8 lambda and minus 10 lambda is minus 18 lambda. 8 times 10 is 80, and I gotta add 1 to that. Lambda squared minus 18 lambda plus 81. And this is, if I did it right, it should factor nicely. This is actually lambda minus 9 squared right there. So what are my lambdas here? Say it again. 9, 9, and 9, right? Exactly, 9, 9, and 9. Now, it never hurts to check our fun facts. Right? The fun facts, remember the fun facts, the trace of the matrix, if I add the main diagonal, 8 plus 10 plus 9, that's 27. My lambdas have to add up to 27. And also the product of the lambdas should be the determinant of this matrix, which is actually 9 times 9 times 9. So, yes, Nathan.
Is this case 2 we're doing?
Okay, I don't know yet. Let's slow down a little bit. Hold on. First of all, do I even know if this is a defective matrix yet? I don't even know if it's defective because just because there's a repeat lambda doesn't mean that the matrix is defective. What do I have to do to decide if the matrix is defective?
On the basis of the eigenspace.
See if this lambda pulls its weight, right? I gotta check the null space and see if the lambda pulls its weight. So let's do that. Let's look at that. Lambda equals 9. I'm gonna do the null space. Very good. So we subtract 9 from the main diagonal of the original matrix. So we do that. I get -1, 1, 0, -1, 1, 0, and -1, 1, 0. There's my matrix. By the way, just to be really clear about this is the matrix A minus 9I, right? That's what that matrix actually is. And do you agree that all 3 rows are the same?
Yes.
Right, so they cross off. I mean, well, you can cross 2 of them off. Right, I could circle a little pivot here. Remember, I like to set up my variables corresponding to those columns. Let's just use X, Y, and Z. So in this case, we actually have both Y and C. They are both free. I'll call them R and T respectively. And then I've got to figure out what X is. I do know that negative X plus Y is 0. Negative X plus Y cancels out. That just means that X and Y are the same. X is also equal to R. And so when I bust this out, how many vectors am I going to get?
2.
2, exactly. So let's write them down. We've got V1, which is maybe 1, 1, 0. And V2 is That's when I bust out the R. And then the V2 is 0, 0, 1. Okay. So with this in mind, now do we know if this is a defective matrix? It is, right? Exactly. So the lambda has a weight of 3, but only gave us 2 eigenvectors. That's what defective means. Agreed? Great review of chapter 7 going on right now. Yeah, so this is a defective matrix. What kind of defective? Is it mixed eigenvalue? Is it regular defective? Or is it super defective?
Regular defective.
It's regular defective because I got 2 eigenvectors here. So let's just write that down. This is the regular defective case. This is regular defective. Okay, so let me go back. I think I'm going to erase this part for the moment. We will write it back down again when we need it. Super defective piece. But let's come back here to the middle and write down our solution. So I've got, x1 of t. Okay, so here's how we write them down, yeah? E to the 9t times the first eigenvector, which was 1, 1, 0. So we get that vector first. And then we also have, I'll go ahead and put x2 of t right here. This one is e to the 9t. And then the second vector was 0, 0, 1. So there's 2 solutions. We need both of those. And now to get the third solution, x3 of t. So I'm using this, all the stuff that's down here, right, in the regular defective part. So it's supposed to be e to the 9t times, now let's just leave a little bit of space here to fill this in a minute. It's going to be w1 plus t times w2. So we'll fill that in. I just want to remind everybody, how this W process works. So we have to choose W1 so that this diagram works. Meaning that if I take 2 powers of A minus lambda I and apply it to W1, it should become 0. So actually the very first thing I'd like to do is find 2 powers of A minus lambda I, right? So leave a little space to finish that over there. We're going to just write down right here, A minus 9I squared, right? We need to work out 2 powers of A minus lambda I. You understand why I'm doing this? It's because I want to make sure that when I choose my W1 and I apply that squared matrix to it, that it will become 0. I got to have the matrix in my hands if I'm going to be able to check that. So here we go, -1, 1, 0, -1, 1, 0, -1, 1, 0 times itself. And guys, if you are still not sure how to do matrix multiplication, you're running out of time. It's already May. So you're going to need to see me really quick about this. Very few people survive 250B unscathed, not knowing how to multiply matrices. So very important that we can do this. So we go across the rows of the first matrix and down the columns of the second one. So let's just see what we get here. As I work this out, I'm going to go across the rows here. I have 1 minus 1 plus 0, that's 0. -1 plus 1 plus 0 is 0. Last column is always actually going to be all zeros for sure, because of that column of zeros there. When I go into the second row, I get 1 minus 1 plus 0, and I get -1 plus 1 plus 0. And in the bottom row, I have 1 minus 1 plus 0, -1 plus 1 plus 0. So it's all zeros, actually. If you work that out, it's just all zeros. Raylene?
Sorry, so the reason why you're squaring it is because you tried squaring it over here, or is it because you're trying to find 2 vectors?
I'm trying to do this diagram here. And remember, every time I follow one of these arcs, whenever I write that notation, it means multiply by this matrix. And I'm going to do it twice.
Oh,
So I have to have the square of the matrix in my hands to sort of know what to expect.
So does that mean the W's can be anything?
There's lots of right answers for the W's. Yes. Well, let me clarify that. W1 can be anything. Once I've chosen W1, I don't get to choose W2. Once I've chosen W1, I have to use the diagram to figure out W2. There won't be a choice there. But you will have a choice here. And in fact, it's a choice that we're just about ready to make in this example. Right? We are going to choose W1. I'm going to let somebody help me with this in a minute. I would like to choose W1 such that what? Such that this matrix kills it. Because this is the square matrix. The square matrix is supposed to kill W1. That's what the picture shows. However, I do not want the original matrix right here. This is just 1 power of A minus 9I. I don't want that matrix to kill W1. Because if 1 power of A minus lambda I kills W1, then W2 is already 0, and you don't really have a W2 there. What's wrong if W2 is 0? If W2 is 0, then look at how X3 looks compared to X2. They're basically the same, right? Because this W1 is just going to be a multiple of the V2, and you won't have 3 linearly independent solutions. Did you see the dance that you're trying to play here? You're choosing a W1 that does not get killed by the first power of the matrix, but does get killed by the second power of the matrix. Yeah.
If there was just the W1, what would make it a multiple of the V2, but why isn't the V2 a multiple of the V1?
The V2 and the V1, well, the V2 and the V1 those are in case 2, these are linearly independent eigenvectors here. They're not multiples of each other. So these are Li for sure. If we had not gotten 2 free variables here, then we would have actually been in the super defective case. We're only in the regular defective case here. It means I've got 2 good vectors that I'm happy with. They're not multiples of each other. And I can build 2 solutions, which is what I did here. I can build 2 solutions with just those 2 vectors, you see. Yeah. And I'm just trying to come up with a third one. That's what this W thing is about. Okay, so I need some help. Can somebody give me a choice? Can somebody give me a vector that will not survive this matrix? By the way, that's pretty easy to choose. Choose a vector that will not survive this matrix, but which will survive this matrix.
1, 1, 1.
Okay, I'm gonna write down the A minus lambda I again. This is the hard part, guys. This is the part we have to really be careful about. I have to put a vector here that is going to survive this matrix. If I put 1, 1, 1 there and I multiply it out, -1 plus 1 plus 0 is 0. -1 plus 1 plus 0 is 0. -1 plus 1 plus 0 is 0. It didn't survive. Right? It did not survive. So the vector 1, 1, 1 would not work here, actually. Sebastian?
1, 2, 0.
1, 2, 0. Let's try it. Let's try and put 1, 2, 0 here. Let's multiply it out. -1 plus 2 plus 0, that would be 1. -1 plus 2 plus 0, that would be 1. -1 plus 2 plus 0, that would be 1. That actually works. Because W1, so if I put 1, 2, 0, that was what Sebastian suggested. If that's W1, so notice what I'm doing, here's W1. That's W1. Now the question is, what's W2? W2 is just this. That's what the diagram is saying. You start with W1 and you multiply it by the matrix, you get W2. Right? So this is actually W2 then. Okay, so then W2 is 1, 1, 1. That makes sense? And by the way, I already know that this W1 will not survive this matrix. Because nothing survives this matrix, right? So again, the dance that you're playing is W1 should survive this matrix, but not this one. Agreed? And let's just fill that in. So we got 1, 2, 0 here, and we got 1, 1, 1 here. One other question for you guys. I mentioned over here that the W2 is supposed to be an eigenvector. Is 1, 1, 1 an eigenvector? It better be, or else my theory is all screwed up. I said over here that W2 should be an eigenvector. So looking at 1, 1, 1, does that look like an eigenvector? Well, I can come back over here and I can say, well, wait a minute, I already thought I did the eigenvectors. Here are the eigenvectors, right? And actually, this is a basis for the eigenvectors. These are not the only two eigenvectors, right? These are just a basis. You can take linear combinations of these and you just get other eigenvectors, right? I mean, an eigenspace is just that. It's a subspace. It's closed under addition and it's closed under scalar multiplication. So I can take these two eigenvectors, I can add them, I can subtract them, I can scalar multiply them, I can do all the vector space things that we've been doing all semester, and I'll get another eigenvector. So let me ask you again, is this an eigenvector?
Yes.
It sure is. It's actually just the sum of these two. Add two eigenvectors, you get another eigenvector. That's called closure under addition, right? You add two vectors in the set, you get a result that's still in the set. So W2 really is an eigenvector. All right, good. So this is legitimate. This makes sense. And so then my general solution, final thing we need to write down then is the general solution to this problem, which would just be x of t equals C1 e to the 9t times 110 plus C2 e to the 9t times 001 plus C3 e to the 9t times the vector 1, 2, 0 plus t times 1, 1, 1. That would be the answer. That makes sense? Somebody asked me a couple minutes ago, could there be other answers that are correct? And you could certainly have chosen W1 differently, right? Just out of curiosity, I'm curious if anybody would have another choice that they might think of for W1.
110, maybe.
Now see, gotta be careful with 110. No, 110, the problem with 110 is that vector will get killed by a minus 9i, right? I'm looking for vectors that will survive this matrix. What's an easy one?
140,
Even easier than that.
130,
Even easier than that.
100.
Keep coming down.
100.
Yes, that's it. 100. Here's the reason that that is such a cool vector to use. What do you get when you take a matrix? Have you guys thought about this before? You just take this matrix here and you multiply it by 100.
A plus B plus C.
What do you get?
The first column.
The first column. Exactly. You just get the first column. So choosing this is like making your life so simple, right? Because if that's W1, then what's W2? It's just the first column of the matrix you're going to multiply by, which it is not the same vector that we got for W2. It's still an eigenvector, right? And so that would have also been correct. It would have been correct to put 1, 0, 0 here, in which case this would have been -1, -1, -1.
I guess you can do that with any position too, like the second, like 0, 1, 0.
I could have used 0, 1, 0, in which case I would have gotten W2 to be this column. So let me now ask you, could I have used 0, 0, 1?
No.
No, because I would have picked off that column of all zeros, which is not what you want W2 to be. Great. Is everybody kind of getting it? See how this works? Lots of right answers, just gotta be a little bit careful when you're choosing W1. Okay, let's do one more example before we take a break today. By the time we get out of here today, we're gonna try every case. I wanna make sure all three of these cases that we practice. Let's do another one. Okay. Great. You know, so when you're checking answers with the back of the book, you just have to be a little bit flexible to realize that, you know, they could have chosen a different W1 and W2 than you did, and so the answer might look different. So trust your instinct about your process, make sure you're comfortable with it, but don't worry about it too much if you don't have exactly the answer in the back of the book. Okay, let's try this one, guys. Let's solve x prime equals ax, where capital A is going to be the matrix 6, 5, 1, 0, 5, 0, and negative 1, 2, 8. Okay, let's try this one. Okay, so just like last time, I'm going to start by trying to get my eigenvalues, right? So I do the determinant of the A minus lambda I, so I'll subtract lambda off of the main diagonal of this matrix again. Subtract off the lambda here. Main diagonal only. Here's what you're going to have. Anybody want to suggest how I would do this determinant?
Cofactor second row,
Okay, the second row, why are you choosing the second row here, Nathan?
zeros.
I have a lot of zeros to work with on the second row. It makes the expansion very simple. So I'm going to expand row 2. You always want to keep your eyes open for which row or column might be the best choice. Okay, and if I expand row 2, you notice that I just have the 5 minus lambda term here in the middle. If I cross off that whole row and column, I get my 2 by 2 submatrix, which has a 6 minus lambda and an 8 minus lambda, and then I have to tack a plus 1 onto the end of that. Okay, I do not want to multiply that all the way out. Otherwise, I will get something that's hard to factor, but I can take the part in brackets and get a quadratic out of that. So lambda squared minus 14 lambda plus 49. So that also factors nicely. This is 5 minus lambda, and then I actually have lambda minus 7 quantity squared. Okay, as usual, we set that equal to 0. And we get our lambdas. The lambdas are going to be 5, 7, and 7. Based on that, do we know yet if our matrix is defective?
No.
We don't know that yet, right? Until we actually check the eigenspace, we don't know. So which of my lambdas would you recommend that I start with?
So
The 7, right? Because that's the guy that's repeating here. So let's try that one first. Let's start with lambda equals 7. Okay, so I'm going to do a null space. Null space here, I have to subtract 7 from the main diagonal of my matrix. So negative 1, 5, 1, 0, negative 2, 0, and negative 1, 2, 1. Okay, looking good so far. I'll go ahead and, I know that this matrix is not invertible. I know I have to be able to cross off a row. I kind of like the middle row because it's so simple. Let's actually keep the first 2 rows and just cross off the third row. We'll get rid of the bottom row here. And so when I label my columns with X, Y, and Z, I can now solve this by using a free variable. So Z is free, I'll call it T. And then if you just look at the middle row of the matrix here, the middle row of the matrix is actually just negative 2 times y. Well, if that has to be 0, then obviously y is 0. So the middle row tells me that y is 0. And then can somebody tell me the x value?
T.
Sorry, what was that?
T.
T, yeah, oh, sorry, x is equal to t, right? Because when you take, right, so hopefully everybody knows how to do these. This is negative x plus 5y plus z equals 0. That's the first row of the matrix. So I put in 0 for y, And then I see that X is equal to Z. Okay, so they're both equal to T. I'm gonna bust out my variable here. And I'm getting one vector. When I bust out the T, I just get 1, 0, and 1. Or so good? So now do we know if the matrix is defective?
Yep.
We sure do, right? Because the lambda came up twice, but we only got one vector out of it. So this is defective. My question is, which kind of defective? Is it mixed eigenvalue? Is it regular defective? Or is it super defective? Mixed eigenvalue. It's the first case right up here, yeah? Exactly. So this is the mixed eigenvalue case for this example. Let's just write that here, mixed e-value. What it came out to be. And now let's work on getting our three solutions. Save the top part of the board here for us to do that with. Oh, and then there's also the other, there's the lambda equals 5. I guess I actually put that one first, didn't I? And in the list here, the lambda that did not repeat is listed first. So we have another lambda we have to do. Maybe before we do it, let's finish this one first. We've got our minds on this lambda first. Let's do that one first. So I've got to do the W thing, right? So we have A minus 7I. That is just the matrix over there. It's -1, 5, 1, 0, -2, 0, and -1, 2, 1. And that's the matrix that I'm going to square. So A minus 7I, I have to square that. Square that out. So I'm going to write it down twice here. So it takes a little bit of writing. I'm just copying the matrix side by side so that I can multiply it together. Good chance to review matrix multiplication. Write that down twice like that. And when I multiply this out, let's just see what happens here. I get 1 plus 0 plus -1, which is 0. -5 minus 10 plus 2, that's actually -13. And then I have -1 plus 0 plus 1, that's also 0. Second row, I have 0 plus 0 plus 0. 0 plus 4 plus 0. And then 0 plus 0 plus 0. Okay, so I get that's the second row. And then finally on the bottom, I have 1 plus 0 minus 1, that's 0. -5 minus 4 plus 2, that's actually -7. And then -1 plus 0 plus 1, which is 0. So there's your squared matrix. So let's understand the W thing one more time. We're going to choose W1, always starting with W1, right? We're going to choose a vector for W1 so that what happens? So that it survives this matrix, but does not survive this matrix. Anybody have a proposal for me? Sebastian?
0, 0, 1.
0, 0, 1. Okay, let's try it. Let's try it. 0, 0, 1. Does that survive this matrix? Let's put 0, 0, 1 right here, and let's multiply this out. When you multiply by 0, 0, so remember this little trick here. When I multiply by 1, 0, 0, I pick off the first column. But if I multiply by 0, 0, 1, I actually pick off the third column. So if we pick off the third column here, we will get 1, 0, 1. So that's good. 0, 0, 1 survived that calculation. Now, does it survive this calculation? It's not supposed to. So 0, 0, 1 here. Does it survive this one? No. Not when you pick off the third column, right? So I think Sebastian came up with a great choice. 0, 0, 1 works really well. It survives the first matrix, but not the second matrix. Following that? Or so good? Okay, so, and then what is W2 in this case? If W1 is 0, 0, 1, then what is W2? It's this guy, isn't it? Because here's W1, you apply the matrix to it, you get W2. So that would be 1, 0, 1. just as a quick check, this is supposed to be an eigenvector. So let's look, what was our eigenvectors over here? Oh, look at that. It's actually, in this case, this is just luck. But we just happened to get exactly the eigenvector that we had originally derived for this problem. It won't always come out like that, but in this case, it happens to do so. Okay, great. So with that in mind, I can write down my first, well, I can write down the solutions. Let me just come up here to the top and start writing it down. Actually, technically, it doesn't really matter what order you put your solutions in, but this would technically give me the x2 and the x3 from up here. Gotcha?
Can we expect finding the W's to be somewhat intuitive in that, like, for example, there,
Uh-huh.
you choose the last row.
The last column, yeah.
I'm sorry, the last column.
Yeah.
It lines up with the 2 zeros in the squared, a minus 7i.
Yeah, I mean, if you might be wondering, can you always pick 1 0 0 0 1 0 or 0 0 1? Turns out you can't always do that, but a lot of times you can. And as long as you're doing that, you're just picking off particular columns. You can also just try random things. You could try, not here, you could try 7, 8, 9 and just see if it works. You know, just see if it works, work it out. -7 plus 40 plus 9, I think that's 42. 0 minus 16 plus 0, that's just minus 16. And -7 plus 16 plus 9 is 18. So if you chose this for W1, then this would be W2. And of course, when you put, oh, but it doesn't work, does it? You put 7, 8, 9 down here, it doesn't work because you get numbers here, you don't get zeros. Okay, so that didn't work. The reason that 7, 8, 9 doesn't work is basically because of this, you really need to use a 0 here. As soon as you put a 0 there, now when you multiply this out, you will get all zeros here. Which is what you need. So you come back up here, so okay, I want to make that a 0, let's fix this. So now it's -7 plus 9, 0, and -7 plus 9, 2, 0, 2. And sure enough, that's an eigenvector. So it's always going to work out in that way. So let's write down the second and third solutions here, guys. So x2 is going to be e to the 9t times the eigenvector, which we got 1, 0, 1. I'm sorry, e to the 7t. This should be e to the 7t times 1, 0, 1. And then x3 is e to the 7t times w1 was 0, 0, 1 plus t times w2, which was 1, 0, 1. So that's x2 and x3. You might be wondering, where's x1? Oh, we have to have the other eigenvalue for that. Any questions on this part before I do the other lambda? Go ahead and erase this, that's okay. Are we okay? These are just what I called x2 and x3 in the notes earlier. Okay, so let's go back and do the other lambda, and then we'll take a break. So lambda equals, what was the other lambda, 5? Okay, so for lambda equals 5, I'm going to do a null space. I write the word null space there. I'm going to subtract 5 from the main diagonal of the original matrix. I get 1, 5, 1, 0, 0, 0, and -1, 2, 3. Great. We know that this is not invertible. Never is. We can always cross off a row. In this case, it's the third row that I'm going to cross off. Or sorry, the second row that I'm going to cross off. And I'm just going to do a quick ERO right here. I'm just going to add the first row to the third row. So there you go. You get something like that. And we just need to solve this out. I have a free variable for z. So z is free. I'll call it t. And then from the bottom line of the matrix, this is 7y plus 4z equals 0. If I plug in t for z and I solve that for y, I will get y equals negative 4/7 of t. Okay. Then I gotta go back to the first row of the matrix. I've got x plus 5y plus z. That should also add up to 0. So if we solve this one for x, right, it's going to be what? Negative 5y, which is 20/7 times t, minus t. So that's going to be, if you just do the math on that, it's going to be 13/7 times t. Pretty sure I have that right. And I bust out my t and I get my vector here, which is 13/7, negative 4/7, and 1. Okay, and so I can make my solution. This is really what I would have called x1, is just e to the 5t times that vector, 13/7, negative 4/7, and 1. So there you go. That is all 3 solutions that you need. And we can now write down the general solution. Okay, let's do it. The general solution, I'll put it here, and then we'll be good to go. General solution is x of t equals c1 e to the 5t times 13/7, negative 4/7, and 1. That's the first term, corresponding to lambda equals 5. Then we move over to the second term, c2 e to the 7t times the vector 1, 0, 1. And then we move over to the third term, c3 e to the 7t times the vector 0, 0, 1 plus t times 1, 0, 1. And so this becomes your final answer. What do you guys think? Seem okay? Question on that? Yeah, go
For
ahead.
C1, can we multiply by 7 to get whole numbers on the first?
This one you could multiply through by 7.
Oh.
Yes, that would be totally okay. If you don't like the fractions, you can clear those fractions out. Good question. Okay. Well, I know you're all dying to see an example of a super defective case, and I do need to show you one so that you're able to do it. But let's take a 10-minute break first. Give everybody a little stretch time. Feel free to head outside for a few minutes. I'll be starting back up again at around 3:20 or so. I'll see you guys in about 10 minutes. Sorry, did I go too fast?
Just at the end.
Oh, I'm so sorry. It's just a matter of copying all the pieces down.
Yeah, I was just a little confused because I was expecting you to put the V into like W and I was ready to leave that space, but then I realized that no, you don't do that on that one.
Not on that one. Yeah, there is no W there. That's right.
What do you? Oh yeah, the parentheses are. Yeah.
Everybody got a copy of the quiz, right? Okay. Optional extra credit quiz. You guys already wrote that down. I'm just putting it back up for our reference here. Quiz here. Yes. Group work. Not really. Be a little careful in that spot for now, I guess. Yes, you're, oh, okay, it's fine. Couple. All right, guys, maybe I'll go ahead and we'll start talking a little bit more here. I put a group work on your front of your desk there during the break. You hopefully picked that up. We may have a few minutes to look at that today in class. If for some reason we don't get around to it, I just want to make sure I passed it out to you. You can always do it on your own. And of course, the solutions are on Canvas and you can just check those out on your own free time whenever you can. But the most important thing we need to get done in these last half hour today is to make sure everybody sees an example worked out of the super defective linear system. It's kind of the messiest case, but in some ways it's really not any worse than the other cases. I just at the top of the board here, I just reminded you of the main information you need for the third case, the super defective case. But it's already in your notes, and I just want to jump into the example here. We're going to try to solve this 3x3 system. I've got my matrix A already given to me here on the board. And one thing I wanted you to notice about this matrix, like normally the first step is to find the eigenvalues, right? That's what we've been doing on all of our examples. It's the first thing we've been doing. But what you might notice about this example is there's not a lot of zeros in the matrix. And there's certainly not zeros in places that are going to be all that helpful. So I could do something like this to you on the test. if I did, what I would probably do is give you a hint. And I might just even just tell you what the lambdas are. Out of the generosity of my heart, right? I might just decide to give you the lambdas. The hint might be lambda equals -2, -2. And then what if I don't give you the third one? Suppose I gave you two of the lambdas, but I don't tell you what the third one is. How are you gonna figure out what the third one is?
Find the determinant.
Sebastian?
Assume it's the same.
Don't do that, might not be. Yeah.
Find the determinant of the original matrix.
We could take the determinant of the original matrix because why?
Or it should be the amount of lambda multiplied by each other.
It should be the product of the lambdas, right? So if I multiply these three lambdas together, I would get the determinant, but what were you gonna say?
I was gonna say that.
That exact thing.
Yeah.
Okay, does anybody have another idea?
Oh, the trace.
That's it, exactly. Even easier than the determinant is the trace. Like, what is the trace of this matrix? If I add up the main diagonal, -1 plus -3 plus -2, the trace is -6, right? So that means that my three lambdas have to add up to -6. So in effect, if I tell you two of the three lambdas, you can figure out the other one by just using the trace, or the determinant is also fine. The trace is a little faster, so I sometimes like to use that one. Okay, so the lambdas in this problem are -2, -2, and -2. Let's take a look at the corresponding eigenspace. So for lambda equals -2, I'm now going to do the null space of the matrix that I get when I, well, subtract -2 from the diagonal of A, but that really means I'm just gonna add 2. So 1, 1, 0, -2, -1, 1, and 1, 1, 0. This is your A minus lambda I, which in this case is just A plus 2I. That's your matrix. And we know that this matrix is never going to be invertible, so we can always cross off a row. I'll basically just assume that I'm going to cross off the bottom row. I'll do a quick ERO here. Cross off the bottom row, with the first row is just 1, 1, 0. And I'm going to take 2 times the first row and add it to the second row. So 2 times the first row, adding that to the second row, I actually get 0, 1, 1. And I've got to circle my pivots here, and I have a free variable, which would actually be Z. So Z would be, let's say, T, which is a free variable. And now I'm going to solve by back substitution for Y. Y would be -T from the middle equation. And then going back to the top row, X is equal to T. So guys, if you're needing more practice on null spaces or whatever, stop by my office hours. Let's get that cleared up. We've been doing that for most of the semester now, and it really needs to be something that you're pretty comfortable with. So I get my null space, and then I just bust out my T to get my basis vector. So there it is, 1, -1, and 1. Okay. Great, so this is super defective, right? I have the same lambda 3 times, and it only gave me 1 eigenvector. So I can write down, I guess I can just write down the x1 of t. It's just going to be e to the -2t times 1, -1, 1. I'll go ahead and do that now, just so I don't forget about it later. Okay. So we are 1/3 of the way done with the problem, basically, but we've still got to find 2 more solutions, and this is where the W stuff comes up. Now, I mentioned earlier today, guys, that with this picture for W3, W4, and W5, if you just ignore the arc that's over on the far left, you basically have a copy of the picture for just W1 and W2. So what you can actually do, and I mentioned this earlier, is you can use W4 and W5 as your W1 and W2 as well. So you can sort of kill 2 birds with 1 stone. You do the work for W3, 4, and 5, and you'll actually figure out what W1 and W2 are in the process. So let's take advantage of that. Now, what am I going to do here, guys, with this diagram? I'm going to choose W3 so that it survives 2 powers of this matrix. This is A minus lambda I right here. So I want my vector to survive 2 powers of it, but not 3 powers of it. So I've got to actually calculate the powers, right? At some point, you just have to stop what you're doing and just say, I've got to calculate the powers of this matrix. So let's look at A plus 2I, let's square it. Okay, that means I'm going to write this matrix down twice. I have 1, 1, 0, -2, -1, 0, and 1, 1, 0. I have to multiply that by itself. 1, 1, 0, -2, -1, 0, and 1, 1, 0. Okay, so we're gonna work that out. I think I'm just going to save the aggravation of working it all out this time. I'm just gonna tell you what it comes out to be. But of course, you wanna make sure you know how to do this. This is just matrix multiplication. I get the matrix -1, 0, 1, 1, 0, -1, -1, 0, 1. Okay, great. And I also need to know what the cube, only in this case do I need to cube the matrix, but I've got 3 arcs going, right? My picture has 3 arcs, so I'm gonna need 3 powers of my matrix. So I can take the squared power that I already worked out, and I just have to multiply one more time by A minus lambda I. So I put that here. Set that up like that, and I have to just multiply that out again. And I am going to save you the aggravation of that as well. When you cube this matrix, guys, it turns into all zeros. Okay, so you can check that. I won't bother to do all of the details of that multiplication right now. That should be what you have. So far, so good. Any questions so far? Just want to make sure I'm going at a good speed here. The whole idea is I want to get going on my diagram. I've got to choose W3. We're now at the pivotal moment. I need to choose W3. So notice I'm skipping over W1 and W2 because I'm going to come back to those later. I want to choose W3 right now. And I want to choose it in such a manner that what? It's going to survive 2 powers of the matrix, but not 3 powers. Right? It's surviving the first 2 powers so that I can get W4 and W5 before eventually it becomes 0. Does everybody understand that? How that works? That's what the diagram is telling me. So I need a vector, guys. I need somebody to give me a vector that will survive this matrix, but not this one.
1, 0, 1.
How about 1, 0, 0, right? 1, 0, 1 actually would die right here. Yeah. Let's try 1, 0, 0. Right? If I multiply that out, I will get the first column of the matrix, right? That's what we were talking about earlier. So you just get the first column. So it survives this matrix, but then of course, if you put 1, 0, 0 here, it will not survive that matrix. Okay, so this is what we want. This is a good choice. I'm going to choose W3 to be 1, 0, and 0. It's not the only correct choice. You just need any vector that's going to survive, this matrix and not this matrix. Okay, so then my next question is, what is W4? One more time.
-1, 1, -1.
Let's remember, this matrix is the square of the matrix. So if I started with W3 and I did the square of the matrix to it, where would I end up? Which is, what vector is that? W5, right? This is actually, so let's skip ahead. W5 is this guy. You see that? Because this is coming from the square of the matrix, right? Yes.
So wouldn't you go back to the original 1, -2, 1, and then put 1, 0, 0 with it to find W4?
So W4, we go back to the original matrix, meaning this matrix.
Yeah.
This is A minus lambda I, and we put 1, 0, 0 on. Is that what you meant?
Yes.
Yes, put 1, 0, 0 here, and what do we get? we get the first column right here. Is this what you were gonna say, Josh?
Yeah.
This is the first column. This is W4. Exactly. W4 is 1, -2, 1. Does everybody understand this? You're just taking the 1, 0, 0 and you're setting it next to a bunch of different things. Right? And that means, what that means is you're grabbing the first column of all three of these matrices. And that's how you're getting your results. All right, great. And then let's not forget, W4 is also going to be our choice for W1. And W5 can also be our choice for W2. All right, so let's write down our solution, x2 of t. Okay, I'm using the notation from right here. X2 of t, this is going to be e to the -2t times W1, which is 1, -2, 1, plus t times W2, which is the same as W5, -1, 1, -1. There's X2. And we have to write down X3. X3 would be e to the -2t times W3, which we chose as 1, 0, 0, plus t times W4. W4 was 1, -2, 1. Plus t squared over 2, this is coming from the notes there on the top of the board, times W5, which was -1, 1, -1. And so here are the X2 and the X3. Does that make sense? Let's just do a quick self-check on this. W5, which is W2, should be an eigenvector, right? Remember the last vector before you eventually get 0, 0, 0 should be an eigenvector. Is this an eigenvector? I can look back to what I had said the original eigenvector was, and I recognize immediately that that one is just a multiple of this one. So it's also an eigenvector. It's not the same eigenvector, but it's a perfectly good choice. All right, great. And so then my general solution. Somebody in my first class asked me, is it okay to not write it all out again? You know how in chapter 8, I would sometimes say you could just like box some stuff. That's totally fine. So you notice I put a box around X1. I've got X2 and X3 in boxes. So if you want, right here, if you just want to say X of t equals C1 X1 of t plus C2 X2 of t plus C3 X3 of t, and you just want to put a box around that and consider that a good enough answer, I am fine with that. Okay, because I can go back, as long as you've labeled everything. This has to be labeled with an X1, an X2, and an X3, so that I can then make the connection there. But that's fine, that's fine. So this is an example of the super defective linear system. This is what happens in a super defective case. Any questions on it? Does it make sense? Again, the choice of W3, we chose 1, 0, 0. There would have been a lot of other things we could have chosen as well. Actually, in this case, you know, we could have chosen, so, okay, you don't need to take any notes on this. Sorry, go ahead.
You know, we chose 1, 0, 0, 33.
Yes,
We have to use the same one to get the before.
we have to use this vector to get the W4, yes. You cannot change W4 or W5. Once you've picked W3, then that sort of starts the domino effect and you create W4 and W5. But, you know, we could have started with a lot of things here. What happens if I start with 7, 8, 9? I'm just curious. I want to try it. So 7, 8, 9, if I started with that, then W4 would have to change. You don't need to take notes on this, guys. I just want to play with this for a minute. So to find W4, I do this, right? So it's just a little harder, but I still do the same thing. I just take 7 plus 8 plus 0, that would be 15. -14 minus 8 plus 9, that would be -13. And 7 plus 8 plus 0, that would be 15. Okay, so there's W4. So you put that right here, 15, -13, 15. Great. Now, what's W5? Well, now I go over here and I change this, right? I put 7, 8, 9 here. And I work it out. -7 plus 0 plus 9, that's 2. 7 plus 0 plus -9 is -2. -7 plus 0 plus 9 is 2. Okay, so W5 would have been 2, -2, 2. Now, still an eigenvector, just not the same one that we got before. And so now you've got a perfectly good different solution. That's what I'm saying, when you're checking the back of the book, you might have something different than what they do, but it doesn't mean your answer is wrong. It just means there's lots of correct answers. So you can have that. Right? And that would also be just as correct. It just looks a little different on paper. How could this also be correct? I mean, it's not the same vectors that we got before.
There are many bases.
There are many bases, exactly. And the point is that what's going to compensate? What if this is Nathan's answer and my answer was the one we got originally? What's going to compensate? What's going to make our answers actually the same is the fact that we have a C1, a C2, and a C3. Those constants can allow us to sort of move from one solution to another, right? So that's basically what's going on. You have infinitely many solutions, but they're just indexed in different ways. Everybody okay with this? Okay, great. So we have just a few minutes left. I'm curious, does anybody have any questions so far about the homework that's due on Friday? I promised that I would take a minute to see. This is sections 9.4 and 9.5. It's a really important assignment. Raylene?
So not for the homework, but for this,
Uh-huh.
if you were to put this in the exam, you would still do the same way, right? Like you would have like one answer, but our answers wouldn't match yours, you wouldn't like take off.
Oh, no, I would not take off points. That's right. I mean, that's why it's hard to grade. I have to sit there and check. And whatever everybody picked for their first vector, I didn't have to go for that. So it's nice when you pick 1, 0, 0, or 0, 1, 0, or 0, 0, 1. It just makes the numbers so much easier. I would not recommend picking this kind of a vector. It's probably going to work, but you're just going to make your head hurt to come up with the rest of the vectors. So that's just my recommendation. Okay, so anybody have any questions though about the homework for Friday so far? My other class had a couple questions, so I just wanted to see.
9.4, number 4.
9.4, number 4. Okay, yeah, let's do that one. I think that might have been one that my other class asked me about as well. So 9.4, number 4. This is just a 2x2 linear system here. We have 1, -2, 5, -5. And we just are being asked to solve the system. There's a linear system that goes with that. And they just want us to solve it. Okay, so what's my first step? Find the eigenvalues. Exactly. So I'm going to take the determinant of the matrix that I get when I subtract lambda off of the main diagonal. It's a little 2x2 system, so I don't mind just sort of multiplying it out. This time it's a quadratic, so I can handle that. There's my AB minus BC formula. And if I work this out, it's going to be a quadratic. Lambda squared minus lambda plus 5 lambda is actually plus 4 lambda. And then I have minus 5 plus 10, which is a total of plus 5. Okay. So this is my quadratic. I, of course, as always, I have to set that to 0. Okay, so far so good. And I'm just going to use the quadratic equation to come up with the roots here. I have negative b plus or minus the square root of b squared minus 4ac all over 2a. So I get those numbers like that. Negative 4 divided by 2 is actually negative 2. And then I have plus or minus. This is the square root of negative 4. And that would be what? Negative 4, when I take the square root, I get 2i, which then gets divided by 2. So it's just going to be an I on that imaginary term. So these are your lambdas. So far, so good. Those are the lambdas. And I'm just going to now find the corresponding null space for the, let's just use lambda equals negative 2 plus I. So I'm gonna do the null space here, guys. I'm gonna do the null space where I subtract lambda off of the main diagonal of A. So I'm gonna subtract -2 plus I. That's gonna give me 3 minus I, -2, and 5. And then if I take -5 and I subtract -2 plus I actually get -3 minus I. You have to be careful. Just be careful with the arithmetic. There's sometimes some double negatives going on and you just gotta get the signs right and all of that. This should be the matrix. Now, it doesn't look like it, guys, but these two rows have to be multiples of each other. The imaginary numbers tend to disguise that. They camouflage the row relationships among the matrix. But these rows have to be multiples of each other because the theory tells me that I've got to be able to zero out a row. The determinant of this matrix has to be 0. So does anybody have you were the one who asked the question, do you
Yeah.
want to have a particular row you want me to cross off?
Probably the first one that you provide, the
Yeah.
second one by 5.
Okay, so just cross off the first row. I would not bother to divide by anything, actually. I would just do my little A-B trick. You remember my little A-B trick? This is where I swap these. This is a good thing to review. I'm glad we're doing this. Remember where you swap these two numbers and you change the sign of one of them? So I put the 5 in the second slot and I put the -3 minus I in the first slot, but I'm gonna change the sign of the -3 minus I. So it becomes 3 plus I. Everybody good with that? Again, if you're wondering what kind of shenanigans I'm doing here, there's the equation. All I'm doing is I'm saying, all right, I'm gonna put a 5 there, and then to make it work, I've gotta put 3 plus I there. So my X and my Y are what I'm putting right here to make this cancel out. It's just the algebra of it. Okay, great. So what we have to do now is write down the corresponding solution. Let me do that here in the middle, I think. Okay, so this is a good review of what we did on Monday. We have to do the whole Floyd thing. Remember that? The Floyd process. By the way, before I go any further, a real quick pop quiz. What's the phase portrait for this? Is it a source, a saddle, a sink, a stable spiral, an unstable spiral, or a circle? It's a, what is it?
Unstable spiral,
Stable.
stable spiral.
This is complex numbers, so it's either a circle or a spiral. Because of this -2, remember this from Monday? This is a negative real part,
Stable.
it's a stable spiral. Okay, sorry, just wanted to pop, this is not part of the question, but I just thought, hey, I may as well pop quiz you on that real fast. It's a stable spiral. In other words, if you were gonna draw the pictures of the solutions, they would look like spirals oriented inward, right? That's the way it would actually physically look. It's like dropping a feather on the surface of the ocean, the feather is gonna go like this. Okay, anyway, coming back to what we need to do for this problem. X of t, remember this is a standard setup. We take our eigenvalue, eigenvector pair, and we write down e to the lambda t times v. And I'm just gonna put in what v is and what lambda is. So we have e to the -2 plus I times t, and then the corresponding eigenvector was 3 plus I and 5. So we just write that like that. And my whole goal now, if you stop right now, you're gonna get at most half of the credit for the problem, probably less than half. Because we got a lot of work still to do. I need to sort of get rid of the I from this answer. So the first thing to do is to pull out the e to the -2t out in front of the whole thing. And then we take the imaginary exponential, e to the it, and we use that Euler identity. So it's cosine of t plus I times sine of t. And then with the vector part, we also split it into a real piece, which would be 3, 5, and an imaginary piece, and we see the I has a 1 on top and nothing on the bottom. So that's stop me if I'm going too fast here. This is how you break up the vector into a real term and an imaginary term. Big brace at the end of that. And now we're ready to do the Floyd process. So at this point, we just write this as e to the negative 2t. Floyd is really FOIL. So I take the first term, cosine of t times 3, 5. That's the first term. But then I'm going to do the last term next because I times I is minus 1. So I get a minus sine of t times the vector 1, 0. So right there is first and last. And then the rest of the FOIL is the outers and the inners, and both the outer and inner terms will have the I on them. So for the outer term, I take cosine of t times 1, 0. And then plus sine of t times 3, 5. And this is your outer term, and this is your inner term. So this is where the Floyd comes from. And now you extract your two real solutions, right? You need two solutions, right? It's a two-dimensional problem. I need two basis vectors, and I'm ready to write them down. The first one, let's just put them here. The first solution, x1 of t, is just literally this first part. Right, you just take the first part. Notice there's no I there. There's no I there anywhere, so we can literally just put our mind at ease and go ahead and write it down. Let's copy it down here. There's x1 of t. And then to get the second solution, don't forget the e to the minus 2t has to be part of that as well. And then what I'm going to do here, guys, is I'm going to grab the outer and inner terms, but without the I. Some people will want to know, why is that legal? Why am I allowed to get rid of the I? Well, remember, you have closure under scalar multiplication. At some point, you can multiply by 1 over I and cancel that. Get rid of that. And now we just have to write down cosine of t times 1, 0 plus sine of t times 3, 5. And that works great. That gives you your two solutions. From there, you just have to write down the general solution. I'll let you guys do that. This is c1 times x1 plus c2 times x2. Oh, you guys are, all you guys with so many phones going on. I'm gonna get to be like, you're gonna be able to show all your parents and everything like, oh, where's my calculus professor? Anyway, any questions on that? Does that help? What you needed to see? Yep, it's good to practice this a little bit. All right, guys, I wish you all well with the next few days of studying. Again, study hard this week. It's gonna make next week easier for you. So let me know how I can help. Try out that group work when you have a chance, the extra credit quiz. And I'll see you all on Monday, if not sooner.
So that's like the last lecture, then, right?
And then Wednesday will be the last lecture next week.
So we're gonna be covering material.
There will be new materials. Yes, there will be a little bit of new material. But
226 pages.
there